Good evening, everyone. I'm fine, Raj. Arshad, I hope now you can hear. Okay, today we don't have a lot of attendance. Okay, but I think we should get started. Sir, how much is gone? Who's gone? No, nothing is gone. We just started right now. I'm still doing hellos. Okay, because fine. So, last time we were solving this example. How are you feeling? I'm okay now. We were solving this example, and I think we did part C. We have to start with part D now, right? Okay, we are going to do D of this question. Please take it. Don't worry. It wasn't anything at all serious, right? Right. Let's quickly start. So we have to solve this D, right? So it says that give the sign of work done. This one, give the sign of work done by external agency, means we have to find work done by external agency, W external, right? In moving a small negative charge from B to A. So let's say the charge is at B, it's negative charge, and we have to move it to A, right? This is also negative, this one is negative, so both of them are going to repel. So what do you think? We'll have to apply force in which direction? Will we have to apply force in same direction of displacement, or will we have to apply force in other direction? In other direction. We have to apply force towards A, right? The force will be towards A, correct? And displacement is also towards A, right? Both are towards A, force and displacement, right? So the work done will be positive, not negative. Ah. I hope you all are not you are not getting confused. There are different things. There is some external force, there is electric force, all right? Here we are talking about external force, right? If the negative charge is over here, right, then the electric force is in this direction. But the external force that we'll have to apply to send it from this point to this point here is obviously towards this negative charge, right? And displacement is also in this direction. So because external force and displacement are going to be having acute angle, then the work will be positive, right? Because it won't go there on its own. You have to send it, right? Okay. I hope, Krishna, that is clear. Okay. I would request all of you to come on time, right? If possible, please join within 1 or 2 minutes at 16, at 4 p.m. exactly. Okay. I know there are network problems today. It's fine. I understand. But please try your best. Okay. Let's go to E then. Does the kinetic energy of a small negative charge increase or decrease in going from B to A? What do you think? If you allow if you allow a small negative charge like this to go from B to A, as it will go towards A, what will happen to its kinetic energy? As the charge negative charge will go from B to A, what will happen to its kinetic energy? Yes. Okay, most of you are getting it right. Very good. Very good, very good. Kinetic energy will decrease. That's right, because of repulsion. Okay, that is only, of course, if you are not applying too much opposite force. Hmm. It depends on the force applied, but if you if you will not apply force, then it will decrease, right? That's the idea by which we are going, right? Otherwise, if you could apply too much opposite force, then obviously it could increase as well, right, Avinash? So your idea is fine, but we are using it for a case where there is no opposite force. Okay, fine. So I think that sums up or finishes this question for us. Let's go to next topic. Okay. So the next topic is going to be equipotential surface. Okay, next topic is equipotential surface. Right. Now, so what is equipotential surface? See, the name is so clear. Equi means equal, right? And potential surface. So equipotential surface, right, is a surface. It may be imaginary, no problem, right? A surface on which every point has equal or same potential, right? A surface, it may be imaginary, right, on which every point has equal potential. That's called equipotential surface. Let's take an example. Okay, first of all, suppose you put a point positive charge here. Okay, and we consider a point A here at a distance r from this charge. Okay, like this you can go in any direction. Okay, like this you can go in any direction if it is distance r, right? And I'm sure you understand that for a point charge, potential V due to a point charge is K Q by R. Suppose this charge is capital Q. So then it only depends on this distance R. So if it's same distance in any direction, right? The potential at A, at B, at C, at D, at E is going to be same, right? So this is an example of equipotential surface. All right. This is an example of equipotential surface, right? So what that means is if you take a point charge around it, if you draw a sphere, then this is a spherical equipotential surface. All right. This is a spherical equipotential surface. Okay. So again, any kind of surface where all points have equal potential is called equipotential surface. Sir, can we say a circle is equipotential surface? You can, right? Caudal, you can say that if there is a point charge, then this circle is equipotential surface. But actually, you can also say that this circle is actually a part of a spherical surface, isn't it? So that's why we don't say circular, we say spherical, all right? Because everything is in 3D, right? Around the charge, it can be in any direction, all right? Not just in a circle, but also in 3D. Okay. So now, this is the basic idea of equipotential surface, right? All points have equal potential. Now let me show you some calculation, all right, which will allow us to understand how our equipotential surface must be closed to one. No, not necessary. It can be any kind of shape. Okay, this is not like Gaussian surface, all right? It can be any kind of shape. Okay, so let's do some calculation that will give us some idea about what is equipotential surface like. See, suppose I'm going to start with easiest case of uniform field, all right? Okay, easy case. Then we will talk about the slightly complicated one. Suppose there is uniform electric field like this, okay, in right hand direction, all right? Uniform electric field. In this case, do you realize that if some charge Q, positive, negative, doesn't matter, right? This is some field created by other charges or other source charges, all right? Okay, and this is some test charge Q, right? So if this test charge Q moves like this, perpendicular to this field, right? Suppose it goes from the point A to the point B. Suppose this test charge moves perpendicular to the field from point A to B. Then we can say that potential difference VB minus VA is equal to negative integration E vector dot dr vector, which you can also write, this is also from A to B. Okay, this you can also write as negative integration A to B E dr cos theta. Fine. This is the basic formula of potential difference. But do you realize that here in this situation, always theta is 90? Okay. Here in this situation, theta is 90. All right. So in such a case, VB minus VA will be 0. In such a case, VB minus VA will be 0. All right. Okay. So that means what we have is VB is equal to VA, right? Okay, that means VB is equal to VA, right? Okay, so what this means is potential at A and potential at B equal. But do you realize that you can carry this further? Suppose instead of B we go to C, instead of C we go to D. So like this, all points over here have same potential, right? Like this, all points have same potential. Then no current will flow between A and B. We are not even talking about current. Harshad, don't try to jump from other chapters into this. But see, this is going to be in 3D, right? Because I can also make a surface like this, which is perpendicular or normal to this electric field, right? So this surface is normal or perpendicular to electric field, right? And you can move anywhere on this surface. Let's say from A you can go to this point, or you can go to this point, but you can go to this point. But however you move, it's always perpendicular to the electric field. All right. Okay. So this is a very important idea about equipotential surface and electric field, right? This is this is very important because every time the electric field is going to be perpendicular, every time the electric field is going to be perpendicular to the equipotential surface, right? That is always necessary. So let's see the general case. Okay, so for that, now we are going to talk about general case. Okay, not uniform, anything, no problem, right? So suppose you consider, first of all, this formula, VA minus VB is equal to negative integration of E vector dot dr vector, right? Okay, from some B to A. See, I've written VA minus VB, all right? So be careful, right? So B is lower limit, A is upper limit, final initial. Okay. So I'm saying that if you would forget about this integration, right, where we actually go from a point A to B, which is far. Instead of that, if we talk about small displacement, okay, suppose we talk about small displacement, then instead of VA minus VB, I should be writing dV. dV for small change in potential, right? dV is for small change in potential. All right. Okay. And dr vector is small displacement. Dr vector is small displacement. So in that case, instead of this integration like thing, difference or small change in potential will become dV. All right. And I will not have to do integration now because this is small. So I will just write this. Okay, now I want you to say yes or no if you have understood this formula. Yes or no? Have you understood what I wrote over here? Why no integration? Because the displacement is small, so no integration required. Okay, we don't need to do any kind of integration. Okay. Or shall I do it at the end? All right. So now, if dV is this is also important formula. Okay, I want all of you to remember. So if we consider this, let's go ahead with that. So for some small displacement, I can write this, and this is equal to this, correct? Okay, where theta is angle between E vector and dr vector, right? So now, if we move on an equipotential surface, right? That means dr vector is on equipotential surface, right? Okay, what that means is, suppose this is some equipotential surface, and let's say there are 2 points A and B on that equipotential surface. then we move from one point to another point, like that. Okay, something like this. Clear? If we move from one point to another point, right? If we move on an equipotential surface, right? That means dr is also on an equipotential surface, right? So in that case, dv is 0. Why? Come on, you tell me. In that case, dv is 0. Why is it 0? If we move on an equipotential surface, dv is 0. Why is it 0, people? Think about it. So here we are considering dv as positive, no problem. It may be positive, may not be, it won't matter. No, Avinash, wrong answer. Yes, Kia, very good, correct answer. No, Swarali, wrong answer. Purvendra, correct answer. Well done. I'm asking you, why do we have this? Read this and tell me why. Very good, Rutva. Correct answer. Jai, well done. No, Harsh, not the right answer. Not the right answer. Devanshi, you got the correct answer. Sakshi, that's not the right answer. I'm not asking about mathematics. In fact, what you are suggesting is what we are going to prove, right? Okay, people, don't forget what is dv. Dv means change in potential, isn't it? Small change in potential.